In our previous lecture, we talked about inverse Laplace transform. In particular, we considered the case that for a given f of s, a function in S domain, which is expressed as the ratio of two polynomials, we saw how we can obtain f of t, and our method was under the assumption that the poles of that function f of s are not repeated. We first wrote that f of s as sum of first order terms, okay? And then once those first order terms are obtained, we easily can write their inverse Laplace transforms, and due to the linearity property, we can just combine all those first order terms to obtain the overall time domain signal f of t, okay? So in this hour, we will talk about the general case, okay? But before moving to the general, well, by general case, I mean the case where the poles need not be simple, okay? So we will allow poles to be repeated. But before starting talking about the general case, let's remember quickly what we saw last time, okay? So this is a quick summary of previous lecture. Okay, so we were interested in the problem of inverse Laplace transformation. Inverse by which we mean, given the transform f of s, obtain the time domain signal. Find f of t. Okay, now the f of s's that we were interested in had the following form. They are rational functions, b0 sm plus b1 sm minus 1 bm sn plus a1 sn minus 1 an. Okay, so what we do is, the very first step is figure out the roots of the denominator polynomial, and those roots had a special name. We call them poles. The roots of the numerator polynomial are called the zeros of this transform f of s. So suppose that this can be written as s minus p1, s minus p2, okay? Since this is a polynomial of order n, we have n poles. So that means we're talking about n first order terms multiplying each other. S minus pn, okay? And we consider the case that n, the degree of the denominator polynomial, is strictly larger than degree of the numerator polynomial. That is, n is greater than m. Such f is called a proper rational function. Okay, f of s is proper. Now, for a proper f of s whose poles are simple, okay, that is, whose poles are not repeated, we saw that this can be written as sum of n first order terms, namely k1 over s minus p1 plus k2 over s minus p2, and so on. Okay, so when poles p1, p2, pn are simple, okay, by which we mean pi different than pj whenever the indices are different. Okay, we have the following. F of s can be written as k1 over s minus p1, k2 over s minus p2, kn over s minus pn. And these scalars, possibly complex, are called the residues of the poles, okay? So Kn is the residue of Pn and so on. And how to compute those residues? We had this very nice identity which allowed us to compute them. Ki, the ith residue, equals, what you do is you multiply f of s, okay, by the denominator of the ith term, which is s minus pi. Okay. And what you do is you evaluate this expression at s equals pi. S equals pi. And residues are easily computed in that way. And once these are known, f of t is k1 times e to the p1t plus k2 times e to the p2t and so on. Then f of t equaled k1 e to the p1t plus k2 e to the p2t kn e to the pnt. Okay. Now, before we move to the general case, let us revisit our last example from the previous hour. Okay, and we'll see another way to approach that problem, okay, which some of you may like. It's a little bit different than computing all the residues, okay? And then we can talk about the general case. So this was our last example from the last hour. Example revisited. Okay, we had the following f of s, 20s plus 60, and we had three poles, simple, s squared plus 2s plus 5. This contains the pole at -1, and the second order term contains a complex conjugate pair of poles at -1 plus minus j2. Okay. 20s plus 60s plus 1, s plus 1 plus j2, and s plus 1 minus j2. And then, since this is proper and the poles are simple, it can be written as we saw k1 over s minus p1 plus k2 over s minus p2 plus k3 over s minus p3. In other words, k1 over s plus 1 plus k2 over s plus 1 plus j2 and plus k3 over the third term, s plus 1 minus j2. Here we have k3, but since k3 and k2, those two residues correspond to the poles that are complex conjugates of one another, once one of them is computed, the other, you don't have to use this method to compute it, the other simply must be the complex conjugate of the residue that you already computed, okay? And the reason for that is we're dealing with functions with, or polynomials with real coefficients, okay? Therefore, here instead of k3, we can immediately write k2 conjugate. Okay, now, using this method, we figured out k1 to equal 10 and k2 to equal -5 plus j5. And we discovered that it's really beneficial to write this in polar form if you want our f of t to look nice. By nice, we mean it doesn't contain any complex coefficients. And this, we saw, can be written as the following radius multiplied by e to the j theta, theta being the phase of this complex number, which was 135 degrees. Okay, 3 pi over 4. And then This is K2, therefore K3 is in polar form the same magnitude times e to the minus j 3 pi over 4. And with that, we can write f of t very easily. Okay, so that yield f of t equals, okay, now this term will give k1 times e to the minus t. K1 is 10, therefore f of t equals 10 e to the minus t plus k2, 5 square root of 2 e to the j 3 pi over 4, then e to the p2t, which is e to the minus 1 plus j2t. And we have the complex conjugate expression, minus j 3 pi over 4 and e to the minus 1 minus j2t. Okay, and then these, since these are complex conjugates of one another, the sum must be a real signal, okay? And that equals, we saw, okay, if this is, okay, if this is z and then this is z star, what we have here is plus 2 times the real part of one of those terms. 5 square root of 2 e to the j 3 pi over 4 e to the minus, okay, okay, let's collect the real terms and complex terms together. So what we have is e to the minus t here, okay, e to the minus t, and then we have e to the j times something, okay, e to the j times, okay, 2t minus 3 pi over 4. Okay, why is this true? Because we're adding two numbers that are complex conjugates of one another, z plus z star, and z plus z star equals 2 times the real part of z. Since the real part of z and the real part of z star are the same, this also equals 2 times the real part of z star, and that's what we did here. 2 times real part of, this is z star. Now that equals what? 10 e to the minus t plus, this is real, therefore we can take it outside the real operator, and that yields 10 square root of 2 e to the minus t times the real part of this complex exponential, j 2t minus 3 pi over 4. And then using Euler's identity, that is e to the j theta can be written as cosine theta plus j sine theta. And we're talking about the real part of this, therefore the real part of e to the j theta must be cosine theta. Okay, so that yields minus t plus 10 square root of 2 e to the minus t, and from here we take cosine 2t minus 3 pi over 4 radians, or minus 135 degrees. Okay, so that's what we obtained last time. And now let's see a slightly different way of obtaining the same result without dealing directly with the complex residues. Okay, and it may be useful sometime, therefore it's good to have that other method. Now, for the same f of s, we will try to figure out f of t, okay, using a slightly different approach. Okay, here is slightly another way. Okay, now the f of s that we were given was 20s plus 60s plus 1 s squared plus 2s plus 5. And the complex poles are coming from the second order polynomial, s squared plus 2s plus 5. Okay, so this equals, we know that k1 over s plus 1, then plus k2 over the second pole plus k3 over the third pole. Okay, but instead of writing the remaining two terms which have complex residues, what we do is we do not decompose this term. We leave it as it is, okay? Meaning that we leave it as a second order term. S squared plus 2s plus 5. And then since f of s is proper, this term must also be proper. The second order, therefore the worst case is it's going to be first order, the numerator. So let's write the numerator polynomial as as plus b. Okay, a and b must be real. Okay, now let's figure out a and b. How we can do that? Well, we can write this as a single ratio where the denominator will equal clearly to this. And then, since those two things are equal, by equating the numerators, you can easily figure out a and b. Okay, so this equals, written as a single fraction, s plus 1, s squared plus 2s plus 5, and then we have this times 10 plus this times as plus b. Okay, and this equals f of s clearly, hence 10s squared plus 2s plus 5 plus s plus 1 as plus b must equal the numerator polynomial of f of s, with this 20, which is 20s plus 60. Okay, two polynomials being equal clearly means the corresponding coefficients are equal, and that will give you two equations for your two unknowns, and you can easily figure out a and b. So a and b turn out to be a equals minus 10 and b equals 10. Now, once we figured out a and b, how do we proceed from there? Okay, so let's rewrite f of s once a and b now, since that a and b are now computed. F of s equals 10 over s plus 1, and we know the inverse Laplace transform of this term. Okay, it's here, 10 e to the minus t, plus minus 10s plus 10 as plus b over s squared plus 2s plus 5. Okay, now this produces complex poles, and complex poles, okay, they mean cosines and sines, okay, like this, possibly multiplied by some exponential, real exponential. Okay, so what we're going to do therefore is we're going to decompose that piece into sine and cosine terms. Okay, decompose this into sine and cosine. So what do we mean by that? We mean the following. minus 10s plus 10 over s squared plus 2s plus 5. Okay, now we want to study this term, because this term we know what to do with. Now this equals, let's first write the denominator polynomial in a form such that we're familiar with that expression. Okay, so that can be written as s plus 1 squared plus, okay, and this one here is 2 over 2, okay, this term, this coefficient over 2, and then plus whatever remains, and what remains is 4, and that's the square root of 2. Okay, now why we have written this in this form is because we know we are familiar with such denominator, okay, s plus alpha squared plus omega squared, that produces terms like e to the minus alpha t times cosine omega t and e to the minus alpha t times sine omega t. Okay, and to figure out the portion of cosine and portion of sine that will be coming from this term, we have to be careful about we have to study the numerator. Okay, in other words, we will now try to write this as c times s plus 1, s plus 1 square plus 2 square plus d times omega over s plus alpha square plus omega square. Now, we know from our earlier lecture set, this will produce e to the minus t cosine 2t, and this will produce e to the minus t times sine 2t. Okay? Therefore, if we can figure out c and d, we will be able to write the coefficients of those sine and cosine terms. And then combining that with this term will give us f of t. Okay, what's c and d? Again, all we have to do is write this as a single fraction. And then it will have the following numerator, c times s plus 1 plus 2 times d. And that must equal this guy here, minus 10s plus 10. And that produces immediately c equals minus 10 and d equals plus 10. Okay. Therefore, without dealing with complex residues, we can write f of s as 10 over s plus 1 minus 10 times s plus 1 over s plus 1 square plus 2 square plus 10 times 2 over s plus 1 square plus 2 square. And now again we have three pieces, and we know the inverse Laplace transforms of each of those pieces, which allows us to write f of t equals, this guy produces 10 times e to the minus t, minus 10 times this guy produces e to the minus t due to this times cosine 2t, and finally this produces 20, excuse me, 10, right, because this whole thing gives us sine, right, e to the minus t times sine 2t, so we have 10 e to the minus t and then sine 2t. Okay, now having remembered the simple pole case, we're now ready to present the general case where the poles are allowed to be repeated. Okay, the general case in our inverse Laplace transform, where poles need not be simple. Simple. Okay. So such a general f would look like some numerator, okay? We don't have to worry about what the numerator is because we're interested in where the poles are. So we have, let's say, a pole at P1 repeated N1 many times. And then we have a pole at P2 repeated N2 many times, and so on. Okay? If they are simple poles, clearly N1 would be 1, N2 would be 1, and so on. S minus PL and L many times. Okay. This can be, first of all, be decomposed into L pieces, okay, and each piece would look like some A1 S N1 minus 1 over S minus P1 raised to the power N1, okay, then plus A2S to the N2 minus 1 over S minus P2 N2, and so on, up to PL. A, L, S, and L minus 1, and over S minus PL raised to the power NL. Okay. Now, if we can figure out the Laplace, inverse Laplace transforms of each of those L terms, we can write f of t as that transform plus that transform, and so on. Now, therefore, the question is, what's the inverse Laplace transform of, or how the inverse Laplace transform of this can be computed? Okay. And for that, we have to observe that this term can be written as, or any term can be written as, let's concentrate on the ith term, ai s and I minus 1 plus so on over s minus pi and I. So the ith term can be decomposed into following simpler terms. Ki 0 s minus pi raised to the power ni plus Ki 1 over the same thing but with degree 1 less, s minus pi and I minus 1, and so on up to Ki and I minus 1 over s minus pi raised to the power 1. Therefore, we have only s minus pi. Okay? And then, once or if we can write this, decompose this into such an I many terms, at that point, we recognize each of the terms as the Laplace transforms of some time domain signals. In particular, this guy produces Ki 0 times t and I minus 1 over and I minus 1 factorial, okay, times e to the pi t. And then this term produces Ki 1 times t and I minus 2 over and I minus 2 factorial times e to the pi t, and so on. This term produces, okay, Ki and I minus 1 e to the pi t. Okay. And then by combining these terms with all the terms coming from other i's will give us f of t for this general f of s. Okay. Okay, so the notation is a little thick, okay, I admit that, but note that with this method we can, well, with this way of looking at things we can obtain the inverse Laplace transforms of a very general class of S-domain functions. Okay. Now, this is all nice, but the main problem still remains, okay, and that's how to compute these residues here, ki0, ki1, up to ki and I minus 1. And here is how, and by writing that down, we will have completed the procedure, okay, of obtaining inverse Laplace transform for the general case. Okay, so the main problem is how to find Kim. Okay, so Ki0 equals S minus Pi raised to the power Ni times f of s. So you multiply f of s by the ith such term. And then what you do is you evaluate that at s equals pi, and that gives you this residue here for the highest order term. And then how about ki1? What you do is to compute ki1, before evaluating this product, you differentiate with respect to s, and then evaluate at s equals pi. ki1 equals obtain the product and then differentiate that with respect to s, s minus pi and I f of s. Once you obtain the derivative, then evaluate that derivative at s equals pi. Okay, and for the ki2, you double differentiate s minus pi, well, this product, but starting from second derivative and so on, a scalar starts to accumulate. Okay, for the second derivative we have the term 2, for the third derivative we have the term 2 times 3, for the fourth derivative we have the term 2 times 3 times 4. So for the nth derivative, what we have to do is you compute this derivative, but then you have to normalize it with a factor of n factorial, okay, n being the number of differentiations performed. So in other words, Kim, the nth residue corresponding to the ith pole is 1 over m factorial, and then you differentiate this product n many times and evaluate that derivative at s equals pi. dm dsn s minus pi and I f of s, and evaluate at s equals pi. Okay. If n, okay, is 1 and I equals 1, that means that pole is simple, then this formula immediately boils down to our formula, our identity that we obtained for the all simple pole case. Okay. Now, the notation looks a little bit complicated, but as we said, we're now covering the entire class of signals that we're interested in. Therefore, it's not that surprising that it's complicated. Now, let's apply this methodology to an example where we have some repeated poles. Here is our example. Compute f of t for the following f of s, which is 1 over s plus 1 to the 3 and s squared. Now the denominator polynomial is of degree 5. 3 plus 2, 5. Okay, so therefore we're talking about a fifth order case. So order 5 means we have 5 poles, and 3 of those poles are at -1, so we have a triple repetition at -1 and a double repetition at the origin for the pole at the origin, s equals 0. So this f of s can be written as sum of 5 terms because the order is 5, and those terms are k10 s plus 1 cube plus k11 s plus 1 squared plus k12 s plus 1. Okay, so these 3 terms are coming from the pole at -1. We have 3 terms because that pole is repeated 3 times. Okay, and then this pole at the origin will produce 2 terms. Okay, we have plus k20 over s squared plus k21 over s. Okay, if we can compute all those 5 residues, we can easily write f of t because we know what the inverse Laplace transforms are for those individual terms. Okay, so let's begin by computing the residues corresponding to pole at -1. k10 equals multiply f of s with s plus p1 cube. Okay, and then evaluate that product at s equals -1 at the pole location. Now this product, since s plus 1 cube here will cancel with s plus 1 cube in the denominator, is simply 1 over s squared. So what we're doing is we're computing 1 over s squared at s equals -1. Which clearly equals 1. Okay, k11. Now what we do is, before evaluating the product at s equals -1, we differentiate it 1 times. Okay, we differentiate it once and divide by 1 over 1 factorial. So therefore that means we don't have to worry about the second residue, about this m factorial thing. And what we have is simply differentiate this product and evaluate it at s equals -1. So we have minus what? 2 over s cubed evaluated at s equals -1, and that produces 2. And finally, for the last residue corresponding to the pole at -1, which we label as k12, what we do is we have to be careful about normalization. Since we're going to double differentiate, we have to divide this thing with 2 factorial, or simply 2. Okay, 1 over 2, and then double differentiate 1 over s squared, and that's 1/2 times 6 over s to the 4 evaluated at s equals -1. That produces 3. Okay, hence these guys are now known. Let's do the same thing for k20 and k21. K20 equals, okay, now we're dealing with this term, s squared. To compute the highest order term, okay, the highest order term's residue, what we do is we multiply both sides with s squared, which will cancel that. We have 1 over s plus 1 cube, and that we evaluated at s equals 0. Okay, K20 equals s squared f of s evaluated at the pole location, which is 1 over s plus 1 cube evaluated at s equals 0, and that gives us 1. And finally, K21 is, before evaluating this, we differentiate with respect to s. 1 over s plus 1 cube evaluated at s equals 0, and that's minus 3 s plus 1 to the 4 evaluated at s equals 0, and that's minus 3. Okay, so we now have all the residues in our decomposition. Okay, the last step, therefore, is to figure out the individual inverse Laplace transforms and combine them into a single piece. Okay, so f of s now equals 1 over s plus 1 cube. Okay, because K10 equals 1, plus 2 over s plus 1 square plus 3 over s plus 1. Okay, those are the terms for the pole at minus 1. Then we have plus 1 over s square, and finally minus 3 over s. Okay, from which we can write f of t as follows. For that, let's quickly remember here, why not, some of the f of t, f of s pairs, and also a property of Laplace transform that we have discovered in our previous lectures. So f of t and f of s, note that for one we have, or for unit step, we have f of s equals 1 over s, and then you integrate this, what we have is t, and what we have here is 1 over s squared. You integrate this once again, what we have here is t squared over 2, and what you do is you divide by s once again, and f of s is s cubed. Okay, and furthermore we have the following, let me squeeze it here. Okay, we have the following property. If you know the Laplace transform of some signal f of t, okay, if you know f of s corresponding to f of t, then the Laplace transform corresponding to e to the minus alpha t times f of t simply is f of s plus alpha. Okay, so that's the relation between f of t, f of t's Laplace transform, and e to the minus alpha t times f of t's Laplace transform. Okay, therefore what we have here is 1 over s plus 1 cube. Now for 1 over s cube we have t squared over 2. So that means for 1 over s plus 1 cube we have to have this guy multiplied by e to the minus t. Okay, so we have for this guy e to the minus t times t squared over 2. For this guy we have 2 times t times e to the minus t, and for this guy we have 3 times e to the minus t. In other words, all these 3 terms can be written as t squared over 2 plus 2t plus 3, and everything is multiplied by e to the minus t. And this term produces t, and finally this term produces a constant term, 3. So that's our f of t for a repeated pole case f of s, given here.